Hello students, let's continue with the next part for a satellite, that is the time period of a satellite. Now, how do you define the time period of a satellite? A satellite is actually performing a uniform circular motion about the fixed planet. It's actually performing a uniform circular motion means it's a periodic motion. So obviously its time of one revolution will be fixed, and that is nothing but called as time period of the revolution. So we can define it as the time taken by a satellite to complete one revolution is nothing but called as the periodic time or time period of the satellite, represented as capital T. So if I consider this as the Earth and an artificial satellite revolving in a circular path, then the time taken for one revolution around the Earth is nothing but called as the time period of the satellite with respect to this Earth. Clear? Now let's understand a formula for time period. I mean, what are the physical quantities on which the time period of this satellite depends? For that, let's consider Earth, and let's consider a satellite which is revolving in a circular path around the Earth. Now let's say the satellite is performing a uniform circular motion, means it is having a fixed time period. Then for one revolution, if I consider, what would be the time? Obviously, by definition, for one revolution the time would be nothing but the time period. And how much would be the distance covered for one revolution? For that circular path, it will be nothing but its circumference. And what is the velocity with which this satellite is revolving? Understand, it's in a circular orbit, so the velocity with which it is revolving would be nothing but the critical velocity. Now, I take a very fundamental concept. You know, speed is equal to distance upon time. So what is time equal to? Time is equal to distance upon speed. In this case, for one revolution, the time is how much? It's nothing but the time period. So as I said, time is equal to distance upon speed. So time here is time period is equal to distance. How much is the distance traveled for one revolution? It's nothing but the circumference. So distance upon speed, circumference would be the distance. So circumference of the orbit upon speed. So as I said, the satellite is moving with a critical velocity, Vc. So we consider the magnitude of this critical velocity. So we get time period is equal to circumference upon critical velocity. Now note, we need to find out what is the time period. So I don't touch that, I keep it as it is. Time period is equal to what is the circumference of the circular orbit. If the radius of the orbit is small r, the circumference is 2 pi r. Upon critical velocity, in the previous module we had done, critical velocity is given by a formula root of gm upon r. Let's substitute that in the time period expression. I get 2 pi r upon root of gm upon small r. Now the numerator small r, I'll take it inside the root and I rearrange the expression. I get it as time period is equal to 2 pi root of r cube upon gm, which is nothing but your final expression for time period of a satellite. Let's further solve this. If I take squaring on both sides, I get it as t square is equal to 4 pi square r cube upon gm. I get it as t square is equal to 4 pi square r cube upon gm. Now notice 4 is a constant, pi square constant, capital G universal gravitation constant, capital M mass of the earth. For this illustration it's a constant. If I remove all those constant and I put a proportionality, I get square of the time period, that is t square, is directly proportional to the cube of the radius, that is r cube. A very important relation, that is the square of the period of revolution of a satellite is directly proportional to the cube of the radius of its orbit. Clear? Now let's find out an alternate expression for time period in terms of acceleration due to gravity, that's small g. For that I go to the fundamental formula again. Time period, you know, is given as 2 pi root of r cube upon gm. If I consider a satellite close to the surface of the earth, then h is negligible and small r is nothing but capital R. So I get it as t is equal to 2 pi root of capital R cube upon gm. Now, acceleration due to gravity very close to the surface of the earth is given by a formula in the previous module we had done. G is equal to gm upon r square. If I take capital Gm on one side, I get Gm is equal to gr square. Let's substitute this in place of that Gm. So finally what I get is time period capital T is equal to 2 pi root of capital R upon G. Is it a constant? Of course yes, because capital R is the radius of the earth, which is a constant 6400 kilometer, and small g is a fixed value on the surface or close to the surface is 9.8 meter per second square. If I put these numbers, I get the final time period for any satellite close to the surface as 84.6 minutes. Similarly, if the satellite is not close to the surface but at a considerable height h, then the alternate formula for time period of a satellite would be 2 pi root of r plus h the whole cube upon gm. Again, if I take gh as the acceleration due to gravity at the height, I can write g of h is equal to gm upon r plus h the whole square. If I rearrange, capital Gm becomes gh into r plus h the whole square. And if I finally substitute, I get the formula for time period of a satellite at a height as 2 pi root of, yes, r plus h upon gh.